Okay, so these are the 2.1 notes, and it's all about describing a location and a distribution. So let's go ahead and break it down. So percentiles, the percentile, and they put like pth for like if you're talking about like 85th or whatever, any percentile of a distribution is the value with p% of the observations less than it. So for example, I'm sure all of you went to the doctor when you were a kid, and the doctor would sit there and tell your parents like, oh, your child here is in the 87th percentile for height, or your child is in the 76th percentile for height, or your child's in the 25th percentile for height. And that's a comparison saying, okay, that's the number of people who are less than that. Of at your age, that's if you're in the 25th percentile, 25% of the people your age are less than your height. Now, easy example here, I am at the 99th percentile of worldwide height. So that's not even for comparing to my age, that's just comparing worldwide. Out of all heights, that 99% of the heights are less than mine. And again, it's actually a little bit more than that. I'm not trying to flex here, I'm just letting you know that if we were actually to break this down, I think the 99th percentile falls somewhere at like 6'4". So I'm at 6'6", that's 2 more inches. Obviously, there's going to be some more people who are between 6'4" and 6'5". This 99th percentile is basically as high as it gets when we're talking in full percentages. We could break it down to like a decimal point percentage. But we don't get to 100% here because we're not doing an or equal to. And the book makes it very clear that for the sake of our book, for the sake of AP stats, we consider it less than. If you do have a value that's equal, well, oh well, you're just going to have to kind of suffer through that. That's one of those things that's a little bit inexact in statistics, but you can live with it, and we can all live with it. It's just something that you have to consider in your analyses. Another example that I had outside of height was just BuzzFeed quizzes. I kill my time by taking BuzzFeed quizzes. It used to be pretty often. I've kind of grown up and I've moved on to the New York Times crossword as a time killer. It's the best sign of my adulthood so far. But when you take a BuzzFeed quiz, there are some of them that obviously, as those of you know from last year who were in my AB class, you can find out what type of bagel you are. There's others where they give you something and then you can compare yourself to others who have taken the quiz. I decided to take an English quiz. I'm a math teacher, so obviously I'm not doing tremendously on this English quiz. And I scored better than 21% of quiz takers. So for this quiz, you could say that I'm in the 21st percentile. 21% of the people who took this quiz did worse than me. Obviously not the percentile I was going for. I really need to brush up on my structure of essays. I need to know that the final paragraph is called a conclusion, not a finale. I probably could have paid a little bit better attention. I know that. I wanted to purposely not do so well so that way I could kind of show you this percentile. All right, cumulative frequency graphs. The book does a really good job of explaining how these are formed. We're really not going to be forming cumulative frequency graphs all that often. They take a lot of time. Even in your homework tonight, the skills that I'm having you practice reading a cumulative frequency graph. I'm a little bit less concerned with your ability to make them. It is kind of a little bit more complicated to make them because you have to think about like, okay, what's the total number of respondents with those total number of respondents, et cetera, et cetera. I just pulled a random cumulative frequency graph off the internet. It didn't really have a ton of information with it. I don't know what this median household relates to. I don't know if this median household income relates to states or countries. My guess is states. But basically, it goes through and it combines all the median household incomes that exist in a certain range or at a certain value, usually within a certain range. And then they talk about how much of the total percentage they make. And then they add that up. So that way the end of the graph is at 100%, the beginning of the graph's at 0%. Technically, the graph should start off the origin. Here it starts very close to the origin, so that kind of lets you know that, okay, if we're talking about states here, 2% of the states or one state have an income at $35,000, and then immediately it shoots up. This 40%, so or at 40 here, like let's say this is 6%. This isn't saying that we've got 6% of households at 40. That's saying that we have got 6% at 40 or less. Just like, for example, at 55, we're somewhere around 70. So we're saying 70% of households have an income of, that's 55,000 or less as a medium income, or as a medium income. So less than 55K is 70% of the households. And you keep on building up until we get to the point where, okay, 100% of the states have 75K or less household income. And we can go through and we can figure out, like here at 55, we're roughly at 70. And then here at 60, we're roughly at 82. So we can say that like 12% of households make between, or 12% have median incomes between 55 and 60K. So we can get a lot of information from these graphs. You do have to kind of pay pretty close attention to what's going on. We can also kind of estimate our quartiles. So here we can estimate that 75% is roughly going to occur like here. We can draw that down. We can roughly estimate that like 25 is going to occur like right about here. We'll draw that down. So like we can assume that our Q1 value is 45 and our Q3 is 56. We can go through, we can figure out those values by looking at their cumulative percentages. We can make some guesses at what's our Q1, what's our Q3. It's not going to be perfect. There's going to be a lot of estimations in that. But again, this is just a graph that gives you a lot of information. Be ready to have any type of question, like how many, like what percentage of people make between 55 and 60K? Roughly, what is your Q1 and Q3 value? Roughly, what is your IQR? So here I know that 11,000 is my interquartile range. I've got $11,000 of median household income between my Q3 and Q1. Just a lot of information you can take from this graph, so be ready for any of it. And then I've got like a brief check for understanding of a couple of the skills. This is directly from your book. I'm just going to answer it for you so that way you know. If you want to pause, look at the questions, make your own attempt to answer, I think that would be a good idea. So pause now. And now I'm going to go into the explanation. So Mark receives a score report detailing his performance on a statewide test. On the math section, Mark earned a raw score of 39, which placed him at the 68th percentile. That means all those 39s are obviously to throw you off. All we care about is the 68th percentile. He did better than 68% of people who took the test, meaning score-wise, raw score. All right, next thing, Mr. Munson, or Mrs. Munson is concerned about her daughter's height and weight, and in comparison to other girls her same age. She uses an online calculator to determine that her daughter is at the 87th percentile for weight and the 67th percentile for height. What this means is that she is heavier than 87% of girls her age, and she is taller than 67% of girls her age. So I'm not going to make any comments on whether or not that's something you should worry about, but you probably want that to be a little bit more in line. If you're a parent, you're probably looking at, if she's in the 87th percentile for weight, you want her at the 87th percentile for height. That would probably have some level of an effect on where she would fall percentage-wise BMI. When you do this in the book, it's just basically looking to explain to you, that it's 87, she's heavier than 87% of girls her age and taller than 67% of girls her age. It's not looking for you to like infer any health or anything. It's not looking for you to infer what Mrs. Munson is. That's just something that's there. So, and kind of relating the idea of, okay, when you become a parent, like what are you concerned with, etc., what matters to you. Questions 3 and 4 relate to the following setting. The graph displays the cumulative relative frequency of lengths of phone calls made from the mathematics department office at Gavelot High last month. About what percent of phone calls lasted less than 30 minutes. So we go here, we go to the 30 minutes and we go up. Okay, that corresponds directly. We'll draw a line over. I can draw a much better, straighter line. So one of the problems with these is you're doing a lot of estimation. I'm going to say that's about 70%. So I'm going to say, since 70%, it's in the 70th percentile, we're going to say 30% lasted longer. So 30% lasted longer if 70% lasted shorter. So estimate IQR. So I'm going to say that right around there is 25%. So then we'll, again, not the straightest lines, a lot of estimation here. So we'll call that Q1 is 12.5. Q3, well, we figured out that that's at 70, so 75 is going to fall just roughly above it a little bit. We'll call that like 31.5. And then my IQR would be, in that case, 19. So we've got our Q1, our Q3, and our 19-minute IQR. So again, there's a lot of estimation there. It's not perfect, but it's right there. Z-scores. All right, so Z-scores are based on standardizing. And to standardize a score, you find its deviation, which is its value minus the mean, and then you divide by the standard deviation. Z-scores are a great way to compare test values. You look at how the student scores based on the standard deviation. So it's not looking at total score anymore. It's looking at how the student is scored based on standard deviation. So for a lot of AP exams where they give fives don't go to a score that you get, fives go to the top 20%, fours go to the next 30%, so on and so forth. They're going to use Z-scores. They're going to figure out what the mean is. They're going to figure out the standard deviation. And then they're going to break down Z-scores to start deciding who gets what score on the test. It's how colleges decide, okay, what is the ACT range and what is the SAT range that we're allowing in? Or what are the ACT and SAT ranges that we want in the school? They're going to go through, they're going to standardize, and they're going to find a Z-score. It takes away, it helps us compare a lot better to the mean, helps us compare with the spread. Positive Z-scores means that it's greater than the mean. A negative Z-score means the value is less than the mean. And a Z-score of 0 means that it's equal to the mean. So let's go ahead and check for understanding here. Z-scores are just kind of a formula that are straight up. So Mrs. Navard's statistics class has just completed the first 3 steps of Where Do I Stand? The figure below shows a dot plot of the class's height distribution, along with a summary of statistics from the computer outlet. Lynette, a student in class, is 65 inches tall. Find and interpret her Z-score. So for Lynette, she is 65 inches tall, and the mean is 67. We have that told to us here. So that means we're going to subtract 67. And then the standard deviation is 4.29. So I'll divide by 4.29. And this means that her Z-score, let me pull out my calculator and do this math really quickly. So that's negative 2 divided by 4.29. And we get negative 0.466. What does this mean? It means that she is shorter than the average height. It means that she's shorter than the average height by less than a full standard deviation, close to a half standard deviation. And we're going to find out more of what that starts to mean when we get into distributions and kind of how we expect things to fall within a normal distribution in the next section. All right, I'm going to go ahead and erase Lynette's. The next thing that we want to do is we want to figure out Brent and what is Brent's Z-score. So Brent has a Z-score, or has a height of 74. We're going to subtract the mean from his 74. And then we're still going to divide by that 4.29. We still divide by the same standard deviation. Plug this into the calculator. And we get a Z-score of 1.63. This means that he's taller than the mean. Compared to his classmates, he's taller. And he's more than a standard deviation taller. He's more than 1.5 standard deviations taller. This tells us that he's actually fairly tall compared to everyone else. When you have a Z-score that's well above 1, you start talking about people who are more, they're taller than average more so. Obviously, any Z-score that's positive is taller than average, but now we're starting to talk about noticeably taller than other people. So we've got that z-score of 1.63. And that's about all we can say. We'll learn more when we start talking about the shape of distribution in the next section. All right, the next thing that we have is Brent is a member of the school's basketball team. The mean height of players on the basketball team is 76 inches, and his height translates to a z-score of negative 0.85. What is the standard deviation? So here we set up that we know what a z-score is. It's negative 0.85. We know his original height is 74. We know that he has to subtract from the mean of 76. And then we've got our standard deviation down here. Our standard deviation will end up being the 74 minus 76 divided by that negative 0.85. So we'll have negative 2 divided by negative 0.85. And we will find that the standard deviation here is 2.85 inches. So obviously the basketball team, taller than your average student population, but then the variance in that height, or the deviation in that height, it doesn't vary as much as the general student population. And when we stop and we ask ourselves, does it make sense that the standard deviation of the basketball team is smaller than the standard deviation of the student population? And yes, it does. Basketball tends to be a sport which lends itself to taller people. We would expect the people on a basketball team to be kind of within at least similar heights. We expect most of them to be at least like 6 feet, etc. Obviously, that's not perfect. That can change. But again, we expect the basketball team to kind of trend a little bit taller and for everyone to kind of be at a similar height versus the average student population where you might have some people at 5'1" and you might have some people at 6'9". So that's going to change. It's going to have a much wider spread. And with that wider spread, we're going to have a higher standard deviation. So that's just a quick little check that you can do. Again, when we're talking in statistics, we're talking about a lot of real world things, and you can kind of draw in some of your own real world knowledge and your own real world inferences to try to decide whether or not an answer makes sense to you. Obviously, this question's not asking for all that information. I'm just kind of saying to myself, okay, this number seems pretty small compared to the average student population. Why might that be? That's okay. You can do that in this class. You can stop and think of yourself in terms of the real world. This is a real world application, is stopping and considering, based on what I know about how things tend to be in the real world, does this make sense? All right, now, transforming data. The book does a really good job using the graphs to show you how to transform data, so it's really, really important that you read. I put the pages down on your notes so that way it's there. But I'm going to go over some basic examples of transforming data just to kind of really hammer home the points of what happens when we do mathematical operations to total sets of data, what values actually end up getting changed, what values stay the same, and by what measures do these values change. So our first example is Jimothy. And Jimothy decides to measure the heights of everyone on his high school's basketball team. He gets all of his data points and finds all of his relevant information. However, on his way home, he realizes he didn't make them take off their shoes. However, he knows each player wears the same pair of Nikes. They did a team order. Therefore, he needs to subtract 2 inches from every player. How does this affect the data? Now, again, the book does a really good job of explaining this, but when we think about it, if we take every single data point and subtract 2, well, that brings everything, it brings every value based on the center, so any center value down by 2. So that means I would take the mean and I would subtract 2, and I would take the median and subtract 2. And that makes sense. If I change every single value by 2, that means that within that average, everything is 2 less. Within the median, that median value is still going to be in the center. If everything's subtracted by the same number, it's just going to be 2 less. That mean is going to be less by 2. Now, what this does not change is it has no effect on my values of spread. And this makes sense. We stop and we think about it. Sure, we've taken 2 off of every single point. And yes, our mean has come down 2. But since everything has reduced by 2, the deviation from the mean has not shifted whatsoever. So my standard deviation is going to stay the exact same. since everything is going to come down by 2, the distance or the total value of my spread is going to remain the exact same. IQR, everything has come down by 2, so the distance between Q1 and Q3 has remained the exact same. My spread hasn't changed when I subtract 2. And if I added 2, exact same thing would apply as well. I would not change my spread whatsoever. My values of center would change with addition or subtraction, but my values of spread don't. Because when we do the same addition or subtraction to every single value, doesn't change the spread, but it does change the mean and the median. All right, next thing we have, example number 2. The basketball coach is not used to seeing heights in inches. They request to see all of the data in feet. So if the basketball coach wanted all the data in feet, that means that we would have to take the mean value and we would divide it by 12. And we would take the median value and divide it by 12, because division and multiplication both affect center values, or measures of center. Well, now this actually has changed the spread. When we divide everything by 12, that means we've made all of these numbers smaller, and it's going to push them closer together. And again, I would definitely make sure you're looking at those graphs the book provides. It also affects measures of spread. So that means that your spread is divided by 12, your standard deviation is divided by 12, your IQR is divided by 12. Again, this makes sense when we reduce all of our values via division to the same amount. That's going to push everything closer together. You have a much more clustered data set, so your spread is going to change. Just like when we have Jimothy's best friend Jillith. And Jillith just transferred from Australia and is used to all of this height data in centimeters, and she's very interested in what this height data is as well. But Jimothy wants to make sure that Jillith is in full understanding of what this data means. So they would have to multiply all their data points by 2.5. But if they multiply all their data points by 2.5, we're going to do the exact same thing where it affects the mean. So we have to multiply the mean by 2.5. It affects the median, or 2.54. So we would multiply that by 2.54. Also, when we multiply, it does affect the spread. So your spread would be multiplied by 2.54. Your standard deviation would be multiplied by 2.54. Your IQR would be multiplied by 2.54, so on and so forth. Again, this is really important, and this saves you a lot of time, because if you're doing conversion, let's say that you're doing a conversion and you've got 90 data points, and at the end of the day, all you need to figure out for that conversion is trying to make a new box plot. You're not trying to do anything special. You're not trying to make a new dot plot. You're not trying to make a new histogram. We're just shifting the box plot. Well, then that means all you have to do is shift your 5-number summary. Shifting your 5-number summary. You only have to apply these things to 5 numbers. You only have to focus on what's going on with your median, your Q1, your Q3, your spread. You don't want to get down in the nitty-gritty. You don't want to do this with every data point. You don't want to have to do a whole new set of calculations when we can work with the values we need really quickly. So if you need to do a quick unit conversion, or you want to look at something in terms of z-scores, or if you want to look at something in terms of like the book provides an example of, we're going to look at it in terms of error as opposed to looking at it in terms of pure guess. When we do those things, we want to try to translate the data quickly, especially our main points. We don't want to get bogged down in the little nitty-gritty details of every single data point and redo an entire set of data, especially when we start getting into data points that are 90, 100, 3,000. We want to do that quick and easy. Last thing is if you perform addition and subtraction and multiplication and division, for example, when you're doing z-score, for example, when you're doing temperature, your mean and median values are affected by both addition and subtraction and the multiplication and division. Therefore, you do everything that the equation has to the mean and the median. This should also be and median here. Standard deviation and spread values, those are only affected by the multiplication or the division. So therefore, you only perform the multiplication or the division to standard deviation and spread values. Finding a percentile are affected by both addition and subtraction, multiplication and division, so you're going to perform both. So if you're trying to figure out where it falls in the percentile range, you're going to have to do both of those as well. All right, so temperature data, I made this up. I tried my hardest to find a good website that would just provide me with temperature data for scene, but it didn't do it. Don't ask me why. I could get averages. I could get some other things. That's data that we can look at down the line. Maybe we can look at real raw data when we start learning normal scores and things of that nature. But right now, as we're learning our basics, I just kind of had to make this up. Now, let's say for August, this is what Racine's data was. We had 31 days. The mean was 81. The standard deviation was 2.4. The low was 63. The Q1 was 71. The median was 76. The Q3 was 80. And the max was 91. Now, what would happen if we moved everything to degrees Celsius? Okay, we're talking to our friend Yehlen, and Yehlen wants to know all of these things. So that means that I would start plugging each individual data point. I would start doing the transformations based on what affects it into the equation for Fahrenheit to Celsius. So to figure out what my degrees Celsius is for my mean, your mean would go from 81, and then to figure out degrees Celsius, you subtract 32, and then you multiply it by that 5/9. This is a formula that I found online. You guys learned it in chemistry, I'm sure. I just go through. And I find that my mean would now be 27 degrees Celsius. My standard deviation, for your standard deviation, all I do is multiply. I don't do the addition because it's a measure of spread. So that's 2.4 multiplied by that 5/9. And I find that my standard deviation is now 1.33. I stop and I say to myself, does this make sense? Yes, it makes sense. Whenever you look at degrees in Celsius, they're always much lower than degrees in Fahrenheit. A degree in Celsius has a lot more, covers a lot more degrees Fahrenheit. So it would make sense that the data is getting scrunched up here, so my standard deviation gets smaller. If I wanted to figure out each individual value, so my low, my Q1 value, etc., I'm going to do everything to that. So for like my low, I would do 63 minus 32 times the 5/9. For my Q1, to figure out what is the exact number of Q1, I would go through, I would do the subtraction and the multiplication. For the median, again, we already know median, measure of center. We've got to do the addition and subtraction. Now that's for each individual data point, because again, Q1 represents a data point, or a median value of 2 data points, just like Q3, or the median, where we might have to take the average of 2 values. However, we're going to interpret it as a data point. We would go through and we would plug each individual data point into these calculations. But then if I wanted to figure out something like, okay, what's my IQR? My IQR here is 9. But again, when I have an IQR and I'm transforming it, this is a measure of spread. Spread is not affected by addition, so that means I would just do the multiplication. So I'd multiply this IQR of 9 times 5/9. That's going to cross out, and my new IQR should be 5. Let's actually go through and test this to see if this makes sense. So I'm going to do Q1. I'll figure out what my new Q1 value should be. So that's 71 minus 32 times 5 divided by 9. And this gives me 20. And then 80. So 80 minus 32 is 48. I'm going to really quickly do my math again to make sure I've got this right. Okay. Okay, I apologize. This was actually 21.6 right here. Q3. And this would be equal to 26.6. And we can see, oh yeah, there's my IQR. That's going to be 5. So we can see how my IQR is only multiplied by the multiplier or the divisor in this case, kind of. It doesn't have the addition affecting it as well. Each individual data point has both the addition and the multiplier. But when I'm talking about measures of spread, all I have to do is the multiplier. So we can see that happening here. All right, converting to z-score. Again, when you convert things to z-score, when you're talking about each individual data point, you're going to go through, you're going to do multiplication and you're going to do division because we're talking about subtracting the mean and then dividing by the standard deviation. When you're finding your new standard deviation, all you're doing is the divisor. And since z-score is based on dividing by the standard deviation, your standard deviation when you're finding z-score should always become 1. Your mean should always become 0 because you're subtracting 67 from everything. Now to find each individual data point, that's when you start doing 60 minus 67 divided by 4.29. And you can go through and figure out, okay, what is my new minimum based on z-score? And that would give us negative 1.63. I could figure out my new maximum based on z-score of the 75 minus 67 over 4.29. We could find that 1.86 is my new top z-score. Median, again, you would have to go through, subtract the mean, divide by z-score. Each individual data point is going to have everything happening to it. It's a little bit easier to remember with the standard deviation, since when you do z-scores, your standard deviation should always just become 1. Your mean should always be 0. And then we're going to change all the other values based off the mean and how it relates to the standard deviation. And I can go through, I can figure out each individual data point here. I can figure out what my new mean to max is. I can figure out what my interquartile range is, 60 minus 60, 63 minus 67 over 4.29. So that's negative 0.93. 69 minus 67 over 4.29. This is negative 0.466. So we've got our new Q1 and Q3. We could have figured out what our IQR is just by doing, so our IQR originally was 6 because it's from that 69 to 63. We would just divide that by 4.29. And we would find that that IQR is 1.399. We look, we can do, and this is a positive, not a negative 0.466. We can do 0.466 minus negative 0.93, and we would find that that is roughly 1.399. So now we've double checked our IQR just to make sense of it. But again, I went into a lot of detail there. I figured out what each one of my 5-number summary plus my mean and standard deviation should be. But when you're converting to z-score, the big thing to remember is whenever you're reporting things in z-scores, your mean should always be 0, your standard deviation should always be 1, and everything should relate kind of within there. So if you're getting a z-score that's like 30, you're doing something off. Z-score is usually fall between -3 and 3. Your mean is always 0, and your standard deviation is always 1. You guys got a homework assignment, please reach out to me with any questions. I think this chapter is kind of a mix of straightforward yet confusing. There are a lot of little rules that can get you bogged down. Make sure you're checking my answer key versus your answers. Make sure you're reading the chapter. And again, reach out with questions sooner rather than later. Have a great night.